Welcome back, everyone. We are going to start session 3 of the workshop now. Harry, you have 10 minutes, and I will let you know when you have 2 minutes left.
Okay, can you see my presentation?
Yes.
All right.
So Henry is going to talk to us from the Galaxy Science collaboration. So go ahead.
All right. Okay, it's been an interesting workshop so far, and thanks to the organizers. I would say galaxies don't vary much, and so by and large, we use transients and variables as signposts of things that we might be interested in, distances or stellar populations. By and large, our science collaboration is more interested in long-term classifications of transients and using them after the fact than in real-time identification. We're also potentially interested in sources that take more than one epoch for detection. So that's probably also not in the realm of alerts, but in the realm of processing several years of data, co-adding, and looking for things that might show up as variable, but you need more than one epoch. There are some interesting subtle effects in galaxies that may show up in difference imaging, probably below 5 sigma. They may be a source of noise if you care about completeness for sources in galaxies. So I'll mention a couple of those. Oops, it is hung. Let me try again. Okay. So science topics, nearby galaxies, distances and stellar populations. We're interested in low surface brightness universe, galaxies that might not be detected except by transients. And then potentially interested in host galaxies and transient properties. I would say there's not that much activity in the collaboration right now on those topics, but certainly in principle, it's of interest to galaxies science. Novae are interesting partly as distance indicators. So there's about 5 per year per 10 to the 10 solar masses. So a Milky Way sized galaxy will have enough novae if it's close enough to get a distance. There's a fair amount of disagreement on how much scatter there is in the maximum magnitude rate of decline indicator. And it may be that machine learning can tighten that up more. They're interesting because they can be detected in a single visit from LSST out to more than 50 megaparsecs. Just using rates, it looks like somewhere around 2,000 galaxies would have nova distances from the 10 years. They'll mostly be sort of around L star, maybe a little bit less, not really much into the dwarf galaxy regime just because there are too few novae per galaxy. For this and other indicators, if 10% of the stars are not in galaxy, which might be sort of what you expect from models of galaxy evolution, there should be about 200 intergalactic novae. Mira variables, so they're not quite as luminous, but there are many more per galaxy, so 22,000 per 10 to the 10 solar masses, absolute magnitudes between -6.5 and -4 in the I band. They'd be brighter in the infrared, so it's I haven't done the calculations, but it may be that Z and Y are preferable. Useful out to maybe 20 megaparsecs or so with Rubin, probably 1,000 galaxies. Interesting there that the mass function favors low mass galaxies here because they're more per galaxy. You don't need that many to get a distance. And so these are potentially interesting for identifying galaxies that might be close by, but just hard to pick out from the background. Down to about 10 to the 6 solar masses. They also, in principle, can be used as age indicators. So the plot on the right shows the LMC clusters, the period versus ages for, I think these are O-type Mira variables. And also they may be signposts of galaxy interactions if you can't see less luminous stars showing up there. This is our own galaxy, and these are the Miras in the Sagittarius stream that are showing up in red there. One of these subtle effects that's sort of interesting is that there are enough long period variables in a stellar population that pixels in nearby galaxies sort of shimmer. If you have if it's close enough that there are few enough stars per pixel. This has been detected, and it's not a very large effect. It's, percent type variations at distance of, I think this is M87 Virgo cluster. So probably doesn't show up in alert streams, but sort of an interesting effect that would be there more in closer galaxies. Microlensing also will show up as noise for some people's projects and potentially as of science interest. It carries information on the mass function, including black holes and neutron stars, which would be fairly long time scale events. The other one that might show up, probably also not a high enough signal to noise to show up as alerts, are emission-line sources, so planetary nebulae, H2 regions, where you've got a strong emission line that dominates even the broadband filter. So differential chromatic refraction will introduce a shift in the position with air mass, which might show up in the difference images. This has been seen and actually used to get redshifts for AGN from Sloan, and it's been proposed to use that for AGN for LSST, but it will also show up as for emission line sources in galaxies. Supernovae, they're useful tools for studying galaxies as well as cosmology. So their time variation or their population variations with stellar populations, they can be signposts of dust, metal production. The typical host galaxy will be around M star, but we do expect hundreds of hosts in dwarf galaxies, and so they're interesting signposts for dwarfs and intergalactic supernovae. And then high redshift signposts. There's certainly a lot of interest in the community as a whole in finding peri-instability supernovae as signposts for very metal poor populations at high redshift. They can be seen out to high redshifts, especially if high redshift populations had very massive stars. And then gravitational lens caustic crossings, in principle, are probes of dark matter, which is of interest, but also potentially finding individual high redshift stars. So just to address the questions that were posed to the science collaborations, how important are the alert streams? By and large, for most of these, the alert streams are not that important, at least the real-time aspect of them. Are brokers important? Well, classifications are important. And so we're particularly interested in what you get from broker-like services, but not necessarily in real time, because the LSST source catalogs don't have the classifications. So we'd be interested in that. Mentioned all the science topics, what informations do we want? So images, classifications, light curves, colors, mean magnitude. If we can be greedy, if somebody else would go, classify all the Miras and get their bolometric mean magnitudes and corrections, that would be great. If not, somebody in the collaboration will have to learn how to do that. The science collaboration in principle could help with brokers by helping figure out what to do with host galaxies, what kind of demographic information one might want to add there. Mostly we don't need real time, potentially for these high redshift supernovae, caustic crossings, those things we might be interested, although I would say it's not particularly active in the collaboration right now. And that's about it.
Thanks a lot for the presentation and for keeping the time. Deeply appreciated. Do we have questions, Matthew?
Well, Francisco has asked a question on Slack, but he's sort of saying that he thinks it was partially answered. Franz Bauer is asking on the chat, will DCR related changes trigger alerts?
I'm not sure I understand the question.
It's not necessarily for you, but maybe it's for someone in DM. But will those actually be sent out as alerts, or will they just be rejected as bogus internally? I'm not sure. Like,
We're
will
attempting-
DCR related effects be part of the brokers to filter?
I can try to take that. So we're trying to build templates that are that model the DCR effect and remove it. That's challenging. It hasn't been done anywhere in practice at scale, and it will take some time to develop and to have enough LSST images to build those models. So I would say initially you should expect there will be bogus alerts caused by DCR effects that we can't model. And those will be issued, but they will have high spuriousness scores.
Can you please spread out the DCR, please?
DCR is differential chromatic refraction. So as stars of varying colors are at lower and higher air mass, they shift preferentially against the sort of other stars. And so if you don't correct for that when you do the subtraction, they create artifacts. So there will be DCR artifacts, especially in the early survey. They will be flagged as spurious, we hope, we expect. But that as the survey progresses, they will be minimized.
Okay, thank you. Do we have maybe time for one more quick question? Do we have other questions?
Michael Woods-Vasey is typing something, but I'm not certain if it's a question because it hasn't appeared yet.
Okay, so we can take the time in the end, and also you can ask Harry on Slack or in the channel. Thanks very much, Harry.